Welcome back, everybody. Today we'll be looking at Physics Paper 5, Feb March 2016, Variant 52. Let's look at the question. A student is interested in bungee jumping, where a person attached to an elastic cord falls from a height and travels downwards to a distance before moving upwards. Different cords are used for different people. A schematic diagram is shown in Figure 1.1. Unlike in paper files, you might get a general drawing as such, which is in real life. For example, a student is jumping off a bridge over here, or it could be getting a laboratory diagram like in the previous video where we discussed um, aluminum ring and a coil where it was a retort stand that is available in the laboratory. You can't create this setup in the laboratory. You can't draw a student jumping off a thing. It's not. So you could either get a laboratory a diagram that consists of apparatus found in the laboratory, or it could be given a general diagram like this, which shows a boy jumping off a bridge with a bungee cord attached to him. Moving on, the student models bungee jumping in the laboratory by using elastic cords of unstretched length of 50 centimeters with different spring constants. An object is attached to each cord. The student investigates the relationship between the distance h followed by the object and the spring constant k of the elastic cord. It is suggested that the relationship between h and k is half times k times h minus L whole thing squared equals to mgh, where L is the unstretched length of the cord. M is the mass of the object falling, I believe. Attached to each cord. And G is the acceleration constant of free fall. Design a laboratory experiment to test the relationship between H and K. Explain how your results could be used to plot a graph with H minus L whole thing square over H on the y-axis. So they've given us the information that we need to linearize the equation. We don't have to do it ourselves, or they want us to do it in a specific way as we see over here, and to determine the value of G. So G is what we must find. It could be the gradient, it could be the constant, it could be the y-intercept, for example. So you have to find it as such. You should draw a diagram on page 3, yada, yada. So this is all, I didn't include this in the previous video, but this is the same for all paper 5s. They will have procedure to be followed, measurements to be taken. These are general bullet points. You could read them, but it's not really important. Yeah, but this tells you how you should answer your paper 5. Just take note of it. I don't see a point in including it because it's the same every time. I've already included the procedure, the measurements to be taken, the control of variables analysis, and the safety in my answer. So there's no need for me to keep it in all the videos if I make them in the future. So let's understand the experiment. This experiment is the application of Hooke's law. F equals to kx. It's just extension of a spring, basically Hooke's law, where it's elastic or inelastic or deformation, etc. In this case, you must investigate the equation that is provided, that they've given. There's not really much theory work going on like the previous experiment paper 5 that we discussed, where we had to think about how the magnetic flux changes, how and whether we have to keep the coil and the current constant. This is actually much simpler. Usually springs or velocity related paper 5s are my favorite because they don't really require too much thinking. They're very straightforward. They just usually application of formula and understanding some general ideas, and they are usually and the safety or the additional points are generally the same for most paper 5s that are considering springs, considering velocity and movement, acceleration, etc. All that. So your SUVAT equations and whatnot, momentum, all that. So moving on, in this case, we must just investigate the equation that is provided. Basically, we must produce a setup and a procedure that tests the equation. The question also gives us the axes to use. Basically, h minus L whole thing square over h is on the y-axis. So rearranging the equation to give the correct linear equation. So we just have to make sure the thing on the left-hand side, or basically the y axis, is h minus L whole thing square over h. So basically divide by h and multiply. You just cross multiply 2 and then divide by k. So you get 2 mg over k. This is not very difficult. It's very simple mathematics. You just have to divide by h, like I said, multiply by 2, and then divide by k. This equation that we get finally is of the form y equals to mx. There's no plus c, or there's no constant in this. It's just y equals to mx. You have to take note that, all right, looking at the equation, the data provided in the question that is highlighted. So you're given different springs of different spring constants. You have to find the relationship between h and k. If you're given different springs, you can change the different spring constants very easily. So in this case, the independent variable should be the springs with different spring constants k. And the dependent variable would then be the maximum height fallen h, and the constant variable would be the mass of the object. If you look at the equation 2mg over k, you're changing the value k. So g must be, and you're finding the value of g. So m and 2m must be constant, because, like, just take note of this tip. In the linear equation, only one value changes. So looking at the equation out of 2mg over k, that's a typo over here, only k changes. Furthermore, we must find the value of g. So that must mean the m must be constant. But if you look at it in a more theoretical way, the mass of the falling object is kept constant for a fair test. The greater the mass, the greater the force on the spring, thus the extension would be greater. And then the value of h, the value of the maximum distance fallen would be greater if you use a greater mass, like compared to 50 grams and 100 grams. The spring would, the elastic cord would extend more if you use 100 grams, for example. Thus, the results would not be comparable. Right, now looking at the setup, we're given a boy falling off a bridge, but if you look, it's not that difficult. Like they said, the bungee cord is modeled by elastic cord in the laboratory, and then we use a load m, or you can call it mass m, to represent the boy. I use the meter rule to measure the height fallen, which is clamped vertically to a retort stand. It would be good to include set squares over here to prove that it's actually vertically drawn. So anything that is strictly vertical, like exactly 90 degrees from the table, or strictly horizontal by 90 degrees, use set squares as in your diagram to prove that it's 90 degrees. Or you could just write it in your final additional point section. But moving on, this is the diagram. One retort stand clamped. As you see that this bungee jumping is falling from a point, so you must clamp it at a fixed point, use the same mass. I said to keep the mass of the load constant, so you must include the mass balance or any other apparatus that you use. So I have to measure the mass m to keep it constant. So I must use a mass balance. Again, so in your answer, after you're done drawing the diagram, start by mentioning all the independent variable, constant variable, and dependent variable in point form. Get it out the way because they're easy marks. So the independent variable is the spring constant k. The dependent variable is the maximum distance fallen h. Constant variable is the mass of load m, and the unstretched length of the cord L. The procedure, this is in brackets, main procedure, because there will be a side experiment that I will discuss later. Using an electronic mass balance or a top band balance to measure the mass of the falling load m or falling mass m, take multiple readings in average. Just include the best practice into your writing. Take multiple readings in average for all values that you're measuring so that you have an accurate reading, you have a reliable reading. Just include it into your answer. You just take a few words, and I would just include it because you get additional points for these things. Use the same mass for all experiments. This is not entirely necessary because I've already included it on top. Use a meter rule to measure the unstretched length of the spring L. Take multiple readings and calculate average length. Setup as shown in attach mass to spring using a hook. I have not drawn a hook, but you can just mention it in your writing. You can always refer to your diagram as setup as shown in the diagram, so you don't have to, so it's just easier. Let go of the mass. Using a video camera to record the distance traveled, replay frame by frame to find the maximum height fallen by the mass. You could include a camera over here that is looking at the distance by the load, distance fallen by the load. But it's not, I just wrote it, so I didn't want to draw a camera, but it would be good if you could just include any additional apparatus into your diagram. Repeat steps 4, 5, 6 and find the average maximum height fallen while keeping the spring constant. the spring constants. I'm missing another word here. This is crucial. If this is it's a guaranteed additional points mark. If you say you keep independent variable constant and then find different values of the dependent variable and take an average, you get a fixed mark. So it's a free mark. Always write it down. Change the spring and repeat steps 3, 4, 5, 6, 7 to find the value of h. This is not necessary, but I include it because it's best practice. Data analysis. Now plot a graph of h minus L holding square over h against 1 over k. Again, you're changing k and this is on the y-axis. If you so you have to plot the y-axis against the x-axis. So you have to plot h minus L over y square over h against 1 over k. Sorry about that. If the graph obtained is a straight line passing through the origin, no constant value. Yeah, so this fits y equals to mx. It's not y equals to mx plus c, it's y equals to mx. And all y equals to mx graphs pass through the origin. So for the relationship to be valid, the graph obtained is a straight line passing through the origin. Gradient equals to 2mg, because 1 over k is the x value, and then gradient will be g equals to gradient over 2m. You divide throughout by 2m to get the value of g. Safety and additional points. Safety, use a safety screen and wear goggles to protect your eyes in case of a spring snaps. A spring or cord snap. So if you have stretched something and all of a sudden it snaps, it will fly back and it could hit your eyes. So you have to use a safety screen or wear goggles. If anything is falling, usually use a sand tray or a cushion to catch the falling mass. You could write either. In our main setup, moving on. In our main setup, we change the spring constant by changing the spring. However, we don't have a quantitative value for k. You can't plot the value of h minus L over h against spring A, spring B. You have to plot it against a quantitative value for k or 1 over k. So we need to set up a mini experiment. You could draw another diagram, but in this case, it's similar, so I didn't include it, but it's always good to include diagrams for secondary mini experiments. So how do you find k? We use Hooke's law, which is F equals to kx. So we know the force because we know the mass that is attached to the spring. So we attach a known mass to the spring, measure the extension x of the spring by calculating the stretch length minus the initial length. Then we rearrange the formula F equals to kx, which is k equals to F over x, and F equals to m mass time. Basically, F equals to the weight of the mass, which is mg. So k equals to mg over x. However, the mark scheme did give you a mark for stating you could read the value of spring constants of the springs given off a chart. I do not recommend this because you could miss out on additional points, and you're just assuming that you're given a chart that tells you the value of the spring constant. So I would recommend you to carry out a secondary experiment, and it makes the most sense to do so. Other points: use a set square to ensure the meter rule is vertical. Trial experiments to ensure that the mass does not hit the surface during extension. This was provided in the mark scheme. Remember that your spring's length is 50 centimeters. So you could include an additional point stating use a mass that ensures that all springs extend and none of the masses hit the table, because once it hits the table, you don't know the maximum extension that has taken place. Or you could attach the spring at a higher point. Keep the starting point constant and use electromagnet setup to drop it from the same height. So if you're dropping something from a higher height that has greater gravitational potential energy, it will cause a spring to stretch more. So to keep the experiment fair, you could keep the starting point constant. And if you want to keep it even more fair, like if you want to make sure it's a fairest test, ensure that you use electromagnet to hold the mass, and you let go of, once you press a button, the electromagnet will switch off and let go of the mass. If you use a human hand, you could let go. Like you may delay or you might accidentally like push the mass while dropping it, or you might accidentally drop it from a slightly higher point than it really does, or while dropping it, it might cause the mass to spin, but as it leaves your fingers. So it's good to include that in your setup. Remove mass and ensure that the length of spring returns to original length. Remember that all Hooke's law only applies when it is an elastic extension or elastic deformation. Ensure that the coil is stretched elastically for Hooke's law to apply. So it's essential for you to check that once you remove the mass, the length of the spring returns back to its original length, and it's not distorted. Use a fiducial marker on the spring, for example, a piece of tape, to measure the extension. So as the spring, as the basically you can attach a fiducial marker over here, and you can measure the length, the distance traveled by the fiducial marker to find the extension. I hope that makes sense. I don't really have a diagram explaining this, but it's basically a piece of tape, and then you measure the distance traveled by the piece of tape as the spring expands, or as the cord expands, which gives you the distance traveled. Drawing the meter rule clamped to the retort stand. I've marked myself here, which is D4, which is basically additional 0.4. You can either mention it in your additional points or just drawing it. Like I said, include all useful apparatus because you get marks for it even if you've drawn it but you don't mention it. Find the average value of H for the cord and video camera method. So these two also give you additional points. And the last but not least, like I said, repeat measurements for dependent value for constant independent value plus average. It gives you marks. These are fixed marks that are allocated for every paper 5. So just include them, and you can get the most marks. So we've come to the end of the presentation. I hope everyone understood this one. This one was a lot easier than the previous one. All you had to do was apply Hooke's law, model this in a laboratory, and rearrange the equation. You didn't really have to think too much about the theory behind it. This usually applies for springs and velocity related practicals. They're quite simple. And usually they're all regarding falling masses. So you have the same additional points of using a cushion, for example, or using a video camera to find the distance traveled and stuff because they're traveling too fast for the human eye to keep up. Remember, try your best to actually imagine that you're carrying out this experiment yourself in the laboratory, and try to find ways that make you comfortable. For me, it's I was using if you've done any such experiments in the laboratory, you realize that it's very difficult to find the maximum height because the mass moves too fast. So you have to use a camera that replays in slow motion, so you can see the exact frame by frame as it reaches the maximum height. You can just take a reading of the image. Next up, also take note of crucial information in the question, 50 centimeters. So you just have to think about it not hitting the table. If it was 10 centimeters, you know the extension wouldn't be that as great. It wouldn't reach the table, but just include that. Try to think it through. You don't have to get every additional point for getting distinction, but just try your best to get the most additional points down while you plan your experiment out. And again, in my data analysis, I didn't include the equation here, but always include the equation that you have linearized in your data analysis part of your answer scheme. Just include it because you are given additional points for them. All right. Thank you so much for watching this. Stay updated for more videos. Please consider subscribing, sharing this video, and liking this if you enjoyed the content. Thank you so much, and goodbye.